And I think we are live. Welcome all.
Hello.
Hi.
All right. Well, this is the Julia GPU programming workshop. I'm Julian Samru.
I'm Valentin Shurabi.
And I'm Tim Bezer.
All right. Well, let's get started. Give me a second to share my screen.
Give it a second. We are not live on Twitch yet.
Sure.
Okay, well, we will see. I will check that in the background.
Oh, yes.
I'll start with a short introduction then on the GPU programming content we'll be demonstrating today. So as I mentioned, I'm Tim Bezer. I work at Julia Computing. And in this workshop, we'll be demonstrating a couple of elements of how you program a GPU in Julia. We'll be starting with a small introduction, this presentation very briefly about how a GPU works, how you can use it in Julia. And then I'll continue with a deep dive of the CUDA.jl package, where I'll gradually introduce how you can use GPUs in Julia using the array programming interfaces, but also how you can write your own kernels and optimize for performance. All of that content, I'm going to demonstrate it with CUDA.jl because I'm most familiar with that package, but it also works with AMD GPU.jl and to an extent also with oneAPI.jl. And we'll be providing the notebooks to do all that in just a second. And beyond that, Julian and Valentin are going to be demonstrating some specific case studies on how you use that functionality to implement image processing functionality, to do some do-it-yourself ML. And we're going to end the workshop with another small deep dive on how you use kernel abstractions, because that's a very specific package for programming GPUs with a specific API, but it gives you some portability across the different backends. So first of all, the Julia GPU organization is the GitHub organization where you will be finding most of the packages we'll be talking about in this workshop, and most of the packages you can use to program GPUs in Julia. However, there's a bunch of packages in there, 41 last I've checked, and not all of them are interesting to you as a user. For example, we have some infrastructural packages like GPU arrays, GPU compiler, adapt.jl, which you shouldn't be using typically. There's some library wrappers that give you low-level access to, for example, OpenCL or Vulkan. But the packages you as a user will mostly be using are the front-end programming frameworks like CUDA.jl, AMDGPU.jl, oneAPI.jl, and also ArrayFire. In this workshop, we'll be focusing on CUDA.jl, AMDGPU.jl, and oneAPI.jl, because those packages are built on a common versatile programming stack that makes it possible to compile Julia code to the GPU. Whereas ArrayFire relies on a C library that doesn't give you the full extent of generality that the other packages do. But in a sense, you can still get some work done using ArrayFire.jl, of course, but we'll be focusing on the other packages. To quickly explain how the stack works, because the packages are all built on a similar base, we start out with the Julia compiler, which emits LLVM code, and that LLVM code is typically compiled for the CPU, generating assembly for the CPU model in your computer. We designed a package called GPUCompiler.jl that repurposes the Julia compiler using the LLVM.jl package to interface with LLVM and generate code that's suitable for the GPU that's in your computer or in your supercomputer or whatever. And the packages I've mentioned, like CUDA.jl, use GPUCompiler.jl to generate code that's suitable for the GPU at hand. And because all of these packages are, in a sense, so similar, they build on GPUCompiler.jl and they use LLVM, they also have similar APIs. And as a result, we've abstracted a lot of common functionality to program GPUs in the GPU arrays package.jl. That's just a sketch of the high-level organization, but most of that doesn't matter because, as I mentioned, you as a user will just be using CUDA.jl or AMDGPU.jl, and all of the infrastructure I mentioned happens behind the scenes, and you shouldn't get in touch with it. So before diving into each of these packages, let's have a very quick look at how a typical GPU works. So this is a schematic describing a typical GPU with some actual numbers from NVIDIA's latest data center accelerator, the A100. So typically you program the GPU, the device, from the host, your CPU, over the PCIe bus. So memory transfers, as a result, are fairly slow because they have to happen over this common bus. And as a result, you should also avoid doing unnecessary copies from the CPU to the GPU if possible. Once on the GPU, you have a lot of global memory that can be used from all threads, and also some cache in front of that. Most GPUs then have multiple SMs, or shared streaming multiprocessors. Those multiprocessors have also a lot of local memory or shared memory, a large register file, and finally many functional units grouped into streaming processors, or SPs. Those are the so-called threads. As you can see, the A100 has over 6,000 of them. However, using all of these threads isn't easy because, for example, the code that's executing can be bottlenecked on any resource. If, for example, your kernel uses a lot of registers, it won't fit, or there won't fit as many on a single streaming multiprocessor, reducing occupancy. So occupancy is the term that NVIDIA gives to how efficiently your kernel can use all of the available threads on the streaming multiprocessor. It's also fairly tricky to provide enough data to saturate these 6,000 threads. You can, for example, be loading from global memory all the time, or you'll be having a lot of memory contention and stalls. But all of that is very specific, and for most users, you actually won't get in touch with all of this complexity because the programming model that we typically recommend users to use are parallel array abstractions. So those abstractions are high-level operations that implicitly expose some parallelism without you as a user having to know how to use that parallelism. For example, if you call the reduce function on a GPU array, that function, the reduce function, will have been implemented by a GPU developer using a lot of the parallelism that the hardware gives you. As opposed to that, you have the SPMD programming model. That's typically how functions like reduce will have been implemented. It's a programming style where you write so-called kernel functions, and those functions are then executed in parallel. It, however, requires quite some expertise because you as a programmer now have to know how you use the parallelism that the hardware exposes to you. And these are the main two approaches on how to use GPUs and how to program GPUs in Julia. And it's also what we're going to be explaining in this workshop. However, of course, there's other ways of programming GPUs. For example, with OpenMP and Poly, it's possible to just write a for loop and expect of the compiler to automatically compile that very sequential for loop into something that can be executed in parallel on the GPU. However, that requires a sufficiently smart compiler. And the way we do it with CUDA.jl and with the other GPU packages is mainly either using parallel abstractions or writing the kernels yourself. Now, all of the content that we'll be presenting is also available on GitHub. And let me enable this banner that it keeps visible for everybody. We have all of the notebooks we'll be demonstrating and talking about. If you want to follow along, you can, of course, download this notebook and use it locally. However, it's also possible to use JuliaHub.com. So JuliaHub is a compute platform, a cloud computing platform by Julia Computing, where it's possible to create instances of cloud computers that have a GPU, and you can neatly use that with, for example, Pluto or Jupyter or VS Code. And the neat thing, at least for this workshop, is if you create an account, you'll get some free credit, $25 to be specific, and you'll be able to use that credit to follow along on this workshop. So let me demonstrate. If you just go to JuliaHub.com, this is the homepage. If you then register an account, I'm logged in, as you can see here. Then you can go to Compute, and you can create a Julia IDE instance by just clicking on the Launch button. So in my case, the launch button is a connect button because the instance has launched already. But if you were to click on launch, you would see this prompt where you can switch to a GPU instance. And as you can see, it's about $1.40 an hour. With the free credit of $25, it should be possible to follow along this workshop. Once that's done, it takes about 10 minutes to instantiate a system with VS Code. You can click on the connect button, and then you'll get a new window where VS Code is running on a GPU-capable node. So as you can see here, I've clicked Start REPL, and then in the REPL, I've entered the package REPL mode and installed the CUDA package. Now I can just use CUDA on the system. For example, I can do CUDA.version info, and you can see that this always takes a while because it initially loads the all of the functionality and the artifacts associated with Julia. As you can see, I have a fully functional CUDA node to work on. And a convenient way to work with this is that you can use revise, and then you can revise the file that you're currently editing, and then you can just execute the main function on this file, modify it as you want, for example, because you're following along the workshop. Of course, it's also possible to load the notebook directly in VS Code and follow along that way. But generally, JuliaHub is a way to get a GPU node for the users among you that currently don't have a local GPU node to work with. I'm now going to kill this instance because I, of course, do have a GPU locally. Yeah, anyway, I can just switch to VS Code. Let me see if I have something else in my slide deck. No, that's it. So this can go. Let's now switch to the GPU programming notebook. So as I mentioned, this is the one you can find on the GitHub link that's currently being displayed in the banner on the bottom of the feed. It's the introduction notebook I'm going to start with. Let me zoom this in a little. If there's any questions, you can just, I'll try to keep an eye on the comment section. I'll try to answer them in line, but afterwards we'll be having a Q&A. You can see the link now on the stream. It's at pigeonhole.at, where you can vote on questions or answer new questions, and then we'll go over them near the end of the workshop. So anyway, let me start by clearing all output. Or the output is cleared already. Yeah. So first of all, the first thing you need to do before using CUDA.jl is, of course, install the package. So doing so is as easy as entering the REPL mode and doing a pkg.add. In this case, I have CUDA installed already, so I can just load the package directly. Once you've done so, calling the version info function from CUDA.jl is a good way to inspect the state of the system. You can see which version of the toolkit has been installed, how it has been installed, because we support both installing from artifacts and using a local CUDA setup. You can also see which driver is currently being used. Starting with CUDA 11.0, we have semantic versioning. So in this case, we have a driver 11.3 that's still supporting a CUDA installation 11.4. You can also see the specific versions of the libraries in use. This first call, if you're doing this locally, it will take a while because it's going to have to download CUDA, and at the point of inspecting the version of cuDNN and cuTensor, it is also going to have to download these libraries, which obviously is going to take a while depending on the speed of your internet connection. But this is a one-time action, and the artifacts will be cached locally. Now, there are some options to influence this installation procedure. If you define environment variables before the initial call to the first CUDA API, for example, by setting Julia CUDA use binary builder to false, we won't be using artifacts, but we will try to use a local version of the CUDA toolkit. Generally, though, that's not recommended. So only do so if you have a valid reason. For example, if you're running on a cluster where you don't have internet connectivity on your compute nodes, then it might be interesting to install CUDA using the module system and setting this variable. It's also possible to influence which version that's being selected by setting the Julia CUDA version environment variable to a valid version string. But again, that's not recommended because CUDA is going to try and figure out which version is the best one to use given your setup. Nonetheless, it's possible to customize the installation like that. So as I mentioned in the introduction, there's generally two ways in Julia to program GPUs, and the easiest ones is using arrays. So in CUDA.jl, we have the QArray type, which you can use to allocate memory and execute operations. Similarly, in AMDGPU.jl, we have rock array, and in oneAPI, we have oneArray. So let me demonstrate that by instantiating a QArray. In this case, I'm going to pass some values from the CPU, 1, 2, 3, 4, and then I'm going to add 1 to every element. As you can see, the QArray type here serves two purposes. On the one hand, it's going to allocate memory on the GPU, and it's going to manage how and which memory is kept alive on the GPU. And on the other hand, it serves as an API to perform operations on the GPU. In this case, for example, I do an element-wise addition by 1, and this is going to be executing in parallel on the GPU. However, there's a warning, and this warning is a typical pitfall for newcomers, and we dub it scalar indexing. So let me just set this hidden value, but you might start working with a QArray by porting the codes that you had written on the CPU using for loops to the GPU. For example, here I've written a for loop that takes every index of my newly allocated QArray and it adds 1 to it, similarly to this broadcast expression. If I execute this, I get this horrible looking warning that's warning me about what we call scalar indexing. And that's because this operation, in a sense, doesn't use the GPU at all. It's going to be executing on the CPU, and it's going to be transferring one item at a time from the GPU to the CPU, performing the addition by 1 and moving it back to the GPU. And that's because, as I mentioned, CUDA.jl or the GPU programming frameworks in Julia aren't auto-parallelizing. So in this case, if we write a for loop and expect it to be parallelized, we will be disappointed because this doesn't use the GPU at all. And as a result, that's why we print this warning to avoid you from writing horribly slow code while you expect to use the GPU. And you can make this more strict by calling the CUDA.allowScalar function. By default, it's only allowed in interactive context. If you use a script, allow_scalar is always going to be off. But for example, here in Jupyter, because we're working interactively, and it's often very interesting when porting code to initially allow scalar iteration and only optimize your code after that. But if you don't want that, you can toggle the setting by calling the allow_scalar function with the argument of false. So if I do that here, scalar iteration, again, by exiting a single element from the GPU, generates an error. It's the same warning, really, but here we get to see the backtrace where we had this problematic behavior. As I mentioned, it can be convenient, though, to temporarily allow scalar iteration. And in non-interactive scripts, you can also do so by wrapping your code in the allow_scalar macro. For example, this is the same scalar indexing, and it doesn't generate a warning, and it's allowed as we expected. So beyond these small demos, the QArray type generally is designed to resemble what you expect from the base array type. That makes it easy to write code that works on array and then port it to the GPU by just switching the type from the base array type to the CUDA.jl QArray type. For example, we have these very familiar looking constructors where we can use undef to allocate some undefined memory. We can allocate and initialize by passing a CPU array to the constructor. We can use convenient functions like copy to, fill, or similar. And these types of functions make it possible to write generic code. That is, code that's not specific to either the CPU or the GPU, but code that will adapt automatically to the type of another array that gets passed in. Now, some functions don't take an array as an argument. For example, the once function or the rand function, you just pass it a number of elements. And for those functions, you can prefix, oftentimes, you can prefix them with the CUDA module because we have specific versions that are GPU compatible or that result in a GPU array. For example, here, we ask an array of once with the same length as the array I've previously defined. And in this case, I do the same, but with random numbers. Now, to generate these random numbers, we use NVIDIA's libraries because NVIDIA's libraries like current and cuBLAS have been well optimized and are pretty extensive. And we do that for most operations wherever possible. For example, if you import the linear algebra package and you call the mul function, which performs a matrix multiplication or a vector multiplication and so on, we will be automatically using cuBLAS where possible. The same applies to the random function, as I mentioned before, where we use current. If you compute the QR decomposition, we will use qsolver. Same with FFTs and so on and so forth. However, we haven't had the time yet because this is a very time-consuming work to integrate all of these vendor-specific libraries to each and every one of the Julia interfaces that users might expect to be available there. For example, it might be possible that cuBLAS has a routine that might be well suited to implement some function in linear algebra, but we don't always have the domain expertise. So at this point, it would be very valuable for people to help out either with CUDA.jl or by improving AMDGPU.jl, having a look at the documentation of, for example, cuBLAS or RockDNN and figuring out how to implement the interfaces in CUDA.jl efficiently using the vendor-specific functionality in, say, cuBLAS and RockDNN. However, to make this as easy as possible, we have implemented, or at least we provide, all of the C APIs from the low-level vendor-specific libraries directly in Julia. For example, the cuBLAS library has this function, cuBLAS isamin, to find the index of the smallest value in an array. And this function is a C API function, but we do expose it within CUDA.jl. So if you just call the cuBLAS dot and then this function name, we will directly be calling out to the cuBLAS C library. And this is very convenient for people with domain expertise, but don't necessarily know how all of the CUDA.jl internals work to contribute to any of these packages and implement some more of the interfaces that we're currently missing. So in this case, as you can see, it finds 3, and that corresponds to the natively implemented function to find the minimal value in an array. Of course, especially cuBLAS is a C library that's fairly limited in terms of which types it supports. So we also need generic fallbacks. And those generic fallbacks are built on the fact that we can compile Julia code for the GPU using GPUcompiler.jl. And that JIT compilation functionality also makes it possible to implement these very powerful higher order abstractions, where on the one hand, you compose a implementation of a function like reduce or broadcast with some user code. So the easiest way to demonstrate that is by using the broadcast function and composing that with an anonymous function that adds 1 to every element of an array. And this is, of course, the written out version of this very succinct dot operation we're all used to. But it generalizes to other operations as well. For example, we have an implementation of a GPU-specific map function. You can also call reduce. We have functions like accumulate. And this is very powerful functionality because on the one hand, we as GPU developers have implemented a very optimized and hand-tuned version of these intrinsics, yet they still allow to compose with arbitrary user code, making it possible to have CUDA.jl or AMDGPU.jl to generate kernels for you, so to say. However, at the same time, CUDA.jl or AMDGPU.jl are no tensor compilers. And that means that the implementations of these abstractions are scalar implementations. They are not arbitrarily fused together. For example, if you do a reduction of an accumulation, that will result in 2 individual kernels being launched. We won't analyze that and generate a single kernel with these operations fused together. On the other hand, that also makes it impossible to perform array operations within another array operation. For example, if we have this broadcast invocation where we perform a sum of a column, that might not work as fast as you expect, because if we benchmark this is going to take a while because it still has to import the benchmark tools package, we will see that the performance isn't great. And the reason for it is that the sum is going to be spawning a single kernel for every column, in this case, 10 kernels. Because again, CUDA.jl is not a tensor compiler that is going to be analyzing this expression as a whole. And now, a simple solution for this is that many of the abstractions that we have also have a DIMS keyword to generalize, at least in this case, the sum to a n-dimensional sum. So by just setting dims to 2, we'll be summing one dimension and leaving the other one as is. And if we benchmark this, we'll see that this is about 10 times faster because it only has to launch a single kernel and not 10 kernels as before. And as you can see here, indeed, we go from 150 microseconds to around 10 microseconds. So the speed up is even greater. In other cases, however, it might not just result in reduced performance, but it might just break compilation. In this case, because we're triggering a GPU broadcast using a CPU input. And once it finishes compiling, we'll see a nasty compilation error because we're passing some unsupported array argument to the GPU where the implementation of broadcast expected scalar arguments. There's a couple of solutions to this if you still want to be able to perform these complicated expressions, and one of them is using Tulio, which is more of a tensor compiler as I've described it before. And with Tulio, for example, you can write these compact Einstein summation notation, which will be compiled into a single kernel that composes all of these operations in a efficient manner. So this might be a solution if you want to do some more complicated expressions where you need to do multiple array operations at every step of another abstraction. However, this might not be sufficient. You might want more control either for performance or because the array abstractions that we have implemented are insufficient for your exact use case or application. And for that, you'll have to resolve to writing your own kernels, so-called kernel programming. And at a very high point of view, kernel programming isn't that complicated. So it's, as I mentioned, the SPMD, single program multiple data programming model, where you write a kernel function, and that kernel function, single program, will be executed multiple times on multiple data elements. That's where the MD multiple data in SPMD comes from. So in this case, we allocate 2 input arrays, 1 output array, and this kernel function will perform a vector addition. And of course, if we execute this function multiple times, there needs to be a way to differentiate between each of the individual iterations of this function. And that's where this I equals thread index.x comes from. This is going to be looking up the current thread index and use that to select which element to perform the vector addition on. So in this case, we use that I to index both our output and our 2 input containers. Then to launch this function in parallel, we use the @CUDA macro, where we specify the amount of threads we want, and voila, we get the output we expected. So again, from a very high level point of view, that is fairly simple. We just need to differentiate between each of the threads that's executing in our kernel function and act accordingly. However, it quickly becomes much more tricky. For example, on one hand, we need to respect hardware limitations because, as I'll demonstrate, you just can't be spawning as many threads as you want. You also need to be efficiently using hardware resources because recall in the introductory presentation I mentioned you can be loading from global memory all the time. And this is exactly what we're doing here. We're loading from our global CUDA memory, and we're not optimizing this using one of the streaming multiprocessor local memories. And sadly, not every operation is also so easy to implement in a parallel fashion. For example, a vector addition is embarrassingly parallel, but when we want to do something more complicated, like a reduction or a sum, it's going to be much more trickier to efficiently use the parallel resources that the GPU has to offer. So let's begin at the beginning, hardware limitations. For example, say we want to execute this vector addition kernel on arrays of 1 million items. If we do so, we immediately get an error invalid value. And the reason is that if we inspect the device attributes, we can see that the device attribute maximum threads per block is 1024, while in this case, we were launching as many threads as our array is long. So that's not going to work. How do we work around this? And the way we do so is by only launching 1024 threads, which is the limit that our GPU supports, but then launch a number of blocks. And each block is going to contain 1024 threads. And we compute the amount of blocks we need by dividing a sealing division, by dividing the length of the array by 1024. Of course, our index calculation becomes a little more complicated because we can just be using the thread index, but we also have to add in our block index multiplied by the size of the block. And we also have to guard our operation from going out of bounds because this division by 1024 might result in a block that contains more threads than our array actually needs. So to prevent this generating an exception, we add a if test. So let's execute this, and this now works as expected. So we've worked around the hardware limitation, at least. However, we've still hard-coded the amount of threads to 1024, and that can still result in some issues because depending on how much resources this kernel uses, for example, if it uses a lot of registers or if it uses a lot of shared memory, then it might not be possible to allocate 1024 threads on a single shared multiprocessor. And that's why it's interesting to use the occupancy API, which is an API in the CUDA API that makes it possible to look up how many threads you can launch at most. And the easiest way to do that is to introspect the compiled kernel object. And we do so by setting launch to false when invoking our kernel with @CUDA. If we do so, you'll see that we get a host kernel object. That's a compiled kernel that has not executed yet. Now we can introspect some things about this kernel. For example, we can query how many threads we can launch at most. And in this case, that's still 1024 because this kernel doesn't use many resources at all. And we can use the occupancy API, which is exposed through the launch configuration function in CUDA.jl to tell us how many threads and blocks we should ideally launch to fully use the GPU at hand. So using this information, we can then accurately compute how many threads we need. In this case, we're going to clamp the amount of threads that the occupancy API gave us with the length of the array. And then again, we're going to do the sealing division to figure out how many blocks we need to launch. And now we can then launch our kernel by passing the thread and blocks as a keyword argument. Do note that we are reusing the precompiled kernel object here, and then our kernel successfully executes. Another issue with GPU programming is that not all of your algorithms and codes you want to execute on the GPU actually map cleanly on the parallelism that the GPU has to offer. And the running example I'm going to be optimizing for the next couple of minutes is a reduce operation. Because in a sense, reduce is inherently serial. You just want to loop every item in your array, and for example, you want to sum it or you want to accumulate it in another way, and then you want to get a single scalar as the output. So if we would implement this naively by creating a kernel function that performs this iteration and only launching a single thread, this would in fact work, and the output is correct. I'm summing 16 elements here. But if we benchmark it on an array of 1024 by 1024 values, we would see that this is horribly slow. So maybe some explanation about this specific benchmark tools invocation here, and specifically this CUDA.add_sync macro is important, because most GPU APIs execute asynchronously. That means they return immediately until you actually need the results. And at that point, you would be synchronizing the GPU. Of course, if you benchmark GPU code, you want to synchronize immediately, because otherwise you're just measuring the time it takes to queue an operation and not the time it takes to finish an operation. So that's why if you use benchmark tools at benchmark, you should probably also use the CUDA.add_sync macro around the GPU code that's executing. And of course, I'm also interpolating my arrays as you commonly do with benchmark tools. And we can see here that our implementation is horribly slow. 60 microseconds for only 1024 by 1024 elements. So one way to optimize this is you might think of spawning a single thread for every array element, and then performing the accumulation atomically by using the add_atomic macro. So do note that this atomic macro is not yet Julia's atomic macro. Julia 1.7 now also has support for atomic operations, but it is the atomic macro from CUDA.jl. So if you would be using Julia 1.7, you would have to prefix this with the CUDA module to be sure that you're using CUDA's atomic operation and not Julia's atomic operation. And in the future, we will be merging both together, but for now, this is something you need to think about. So again, let's execute this new kernel. We get 136 again, which is the expected result. And if we benchmark this, we'll see that performance has greatly improved. It goes down from 60 milliseconds to, and this is taking a while, to 1.7 milliseconds. So that's an enormous improvement, but it's still horribly slow. If we were to compare to a CPU implementation, which takes a couple tenths of microseconds, we're not using the GPU efficiently here. And that's because this atomic operation effectively serializes the only operation we perform in this kernel, because in the end, we do still need to perform this operation atomically. And this is then a typical example of having to use a parallel algorithm to efficiently implement what is otherwise inherently a serial operation. So in the case of reduction, what we can do is we can launch threads that don't immediately require synchronization by, for example, performing atomic writes to the global memory. But every thread can reduce a couple of elements of its own, and in a tree-like fashion, we reduce that until we only find a single value that we will then write out to global memory. So this is nice in principle, but implementing this is not that straightforward. So let's start with a simple version that reduces within a single block. So again, within a single group of threads that executes on a single streaming multiprocessor. So how do we do this? This is a typical implementation of a parallel reduction where every thread is going to be adding a value next to each other. as you can see here, using this D value. It's kind of an offset, which gets multiplied by 2 on every iteration. And then at every step, a couple of threads become idle until the while loop finishes and we have the reduced value in the end. And this is much clearer if you just add a print statement. And there you can see the activity of every thread at every iteration. And this also shows that it's not bad per se to have loops in your GPU code, but generally what you have to watch out for is that every iteration of your kernel function behaves identically. That's something called thread divergence, and I'm not going to be diving more deeply into this. But if each of your instance of your kernel functions perform radically different operations, for example, some have exited the loop while others haven't, then you're effectively serializing your loop and you will be spending much more time executing this code than you expect. But in this case, our loop is not divergent, and we finally get the expected result, the 136 on thread 1 written to the final output value. In order to extend this to the grid, because we're currently only reducing within a single block, there is a problem, because generally, you cannot synchronize between different blocks, between different groups of threads on the GPU. They might be scheduled in whatever way you the GPU wants. And a simple way to work around this, or at least to cope with this, in the case of reduction, is by just first performing a couple of iterations to reduce values across so-called multiple blocks, and then doing the parallel reduction again in the single block. Valentin, I'm going to mute you if that's okay.
Sorry, I just wanted to point out there are a couple of questions about the kernel material on Pigeonhole. Maybe we take a small break and you answer a few of them.
Yes, that's a good plan. Let me refresh. One question is, what does @qprint line does? Let me go back to that code. This is much like the print function we have in base Julia, where you just pass it a string that gets written out to standard output. However, because on the GPU side, we currently do not support threads, we implement it using a macro. But other than that, it behaves virtually the same to the print function in base Julia, where you can pass it a string, you can interpolate values in the string. For example, here I'm interpolating the value of the thread variable. I'm also interpolating the value of the index and so on. And as a result, we get this output visualizing how our kernel function is processing these values in parallel. There's a question about whether there's, generally speaking, a difference between trying to write programs for threads on the CPU compared to the GPU. At the high level, there isn't, and that's why, for example, Intel's ISPC compiler or OpenMP give you a pretty similar API to working with CPU threads and GPU threads. However, in the end, there are a couple of stark differences. For one, you have many more threads on the GPU than you have on the CPU. For example, on the A100, we had over 6,000 threads, which might shift the trade-offs, whereas on the GPU, you typically want to do a lot of very lightweight work. With CPU threads, you might want to do some more heavyweight work. And of course, when you're optimizing your implementation, you will have to use some of the GPU-specific resources, such as shared memory or intrinsics to send values from one thread to another that aren't generally available or interesting to use on the CPU. Now, a framework like ISPC or OpenMP doesn't have doesn't have any issue with that because they automatically parallelize your code. But in the case of writing a kernel in CUDA.jl or another kernel function with AMD GPU.jl, you generally would be using these resources explicitly. And as a result, kernels would look somewhat different than they would on the CPU. All that said, we do have a package that's kernel abstractions.jl, making it possible to abstract away some of these differences and let the framework take care of that for you, making it possible to write kernels that execute efficiently both on the CPU and the GPU. And Valentin will be going into that near the end of the workshop. There is a question about iterating over threads and blocks where the thread index varies fastest. Is this ordering important for performance? It is, but it's not necessarily important in the same way than it is on the CPU. Generally, what you have to take into account on the GPU is that the data elements that are being accessed by consecutive threads, so for example, if thread 1 is accessing array element 1 from array A and thread 2 is doing the same to element 2 of the array, where so consecutive threads are executing consecutive or accessing consecutive memory items, then the GPU will be able to coalesce these memory accesses. And that's actually a very important way to improve performance on the GPU. For example, this is then a best case where the GPU, its memory manager will be able to coalesce many of these memory accesses together into a single operation on the memory bus. And that's not the case on the second iteration, for example. So that might be a way to improve some of your kernels, making sure that threads access your array elements in a coalescible pattern. However, it doesn't necessarily matter as much on the CPU to do it across statements. It's mostly important to do so across threads. There was another question on how is the maximum number of threads and number of blocks a kernel can use calculated. So that's using the occupancy API, and it does take into account the current active device, and it's going to be querying, for example, how much shared memory your kernel uses, how much shared memory is available on your GPU, and figure out how many threads can be launched at most. The amount of blocks the occupancy API returns, let me scroll back. The amount of blocks here is not the amount of blocks that you need to launch, but it's the amount of blocks that you need to launch if you want to fully make use of the GPU. So this is not a value you need to take into account, but if you have a kernel that, for example, can choose between either launching more blocks or iterating in a loop, then you might prefer to launch at least 48 blocks in this case to make sure that you're efficiently using the GPU. Concerning accuracy between GPU and CPU methods, generally the issue with comparing a CPU and a GPU implementation is not necessarily that the accuracy of the individual operation differs. All of that is documented in the CUDA programming guide, but the problem is that the order of operations is different. For example, in the serial reduction, we're going to be reducing in a well-defined order, whereas the parallel GPU implementation might be executing the reduction in a different order every time. And that's something that oftentimes influences accuracy when you're comparing to a CPU implementation. And I think I've answered most of the questions pertaining the material I've just presented at this point. So let's continue for now. Where was I? Right. So in this case, I think the last point I still had to explain, or did just explain, is how we generalized our parallel reduction that reduces the value in a single block to an implementation that reduces across a number of elements that doesn't fit into a single block by adding a loop to our kernel that first does a local reduction of multiple values across our array before doing the local reduction of parallel values in a single block. So let's execute this to see whether we get the expected result. We do, and then let's benchmark this. And just to recall, the last implementation was 1.7 milliseconds, which was using atomic operations. And now this parallel implementation has dropped to 90 microseconds. So this is another very significant improvement because we're avoiding this synchronization of all of these atomic operations, and we're now more efficiently using the parallelism of the GPU. But as you can see, we are only launching a single block of 1024 threads. Whereas, as I just explained a while back, you need to be executing a number of blocks such that the GPU can switch between threads. And the occupancy API gave a number of 48 for the previous kernel, but in this case, for this kernel, we'll also be having to execute a couple of blocks at the least for this to execute efficiently. So let's remove that loop that performed the reduction across values that didn't fit into a single block. And let's go back to our atomic addition we used to have in the initial implementation. However, now we're not doing this atomic operation for every element anymore. We're first reducing within a single block, and then we'll be performing a single atomic reduction, one for every block. Let's make sure this executes well. It does, and performance should be a lot better. So just to recall, performance was 92 microseconds. Now we are at 45 microseconds. I'm going to speed up a little because this is probably not relevant to most of you, but it does demonstrate some of the concepts that you need to think about when programming kernels. Another thing I mentioned is that you should be efficiently using the GPU's resources. Our previous kernel was always loading memory from global memory, whereas the shared multiprocessor also has some shared memory that can be used as a buffer. And so now we'll first, at the start of every block, load a couple of values in shared memory. We'll be doing this cooperatively. So every thread is going to be loading a couple of values. And then we will be using this shared memory without having to round trip to global memory all the time. So our block local reduction will now happen without having to send memory to the GPU itself, but the memory from the streaming multiprocessor will be able to cache all of these accesses. And then we still do the atomic reduction we did before. Let's execute this to make sure it's okay. It is. And performance should again improve. So recall, performance was 45 microseconds. Now we are at 44 microseconds. And you might wonder, how come? This is a very small reduction. And it is, but that's because I'm using a very recent GPU, as somebody noted in the comments. If you would do this on an older GPU, for example, I'm temporarily going to switch to one of the older GPUs I have in my computer by just calling the device bang function passing 1, switching from device 0 to device 1. And if we then execute both of our kernels, so the regular atomic one and the atomic one with shared memory, we'll first see that performance is a lot slower. So GPU generations typically have a lot of performance improvement, especially for the generic code that we are writing. So the non-shared memory implementation executes in 300 microseconds, while the one using shared memory only requires 220 microseconds. This to demonstrate that the shared memory optimization is very useful for older hardware, but might be less relevant for very high-end recent hardware. But again, as I mentioned, I'm going to stop my deep dive here, at least of this reduction implementation. For example, you could still tune the launch configuration. You could use dynamic shared memory. You could avoid shared memory bank conflicts, as somebody notes in the comments. You could use warp intrinsics to more efficiently communicate between threads within a lane. You could make sure that all of the memory accesses are coalesced, as I mentioned before on one of the questions. And you can see that if you execute our baseline sum implementation in the CUDA.jl package, which by all means isn't extremely optimized, but nonetheless, it still squeezed out some more performance. So it's 38 microseconds, whereas our optimized implementation clocked in at 44 microseconds. And just for reference, if we compare that to the base implementation where we reduce on the CPU, this comes in at 80 microseconds. So we're significantly outperforming the CPU here. Of course, in a way, this is unfair because we're not transferring memory to or from the GPU. If we were to do so, then there would be a significant additional performance penalty because transferring 1024 by 1024 elements is also going to be taking some microseconds. However, for many of your applications, you will be keeping your data on the GPU all the time. So it's not that unfair, at least, to only look at the performance of a kernel function without including the time it takes to transport memory. Another question I just see coming in is whether it's possible to access the metrics about global load and store metrics efficiently. And for that, I'm going to be demonstrating the profilers that the CUDA toolkit comes with. It's currently not possible to access these metrics, these performance metrics and performance counters from within Julia. We don't have the APIs to do so, but the profiler tools are sufficiently powerful to make it easy to do so using those external tools. But before that, I'm going to have a quick look at the pigeonhole to see whether there's additional questions. There's a question about optimal data structures, array structures, or structures of arrays. Generally, it depends on your access pattern. But again, what's going to be mattering here is whether you access a field of your structure or your structure as a whole. And if you do so, you need to think about whether the memory manager will be able to coalesce these accesses. So if you're accessing a field and you're accessing that field across all threads, then you probably will want to make sure that those fields are next to one another in memory so that the memory manager, again, can coalesce these accesses. And depending on that, either array of structures or structures of array can be the more suited layout for that. There's a question about which book would be recommended for kernel GPU programming. A book I typically recommend is CUDA by example, even though it's the examples are written in CUDA-C. At least it gives you a nicely paced introduction to the various features that CUDA has and which ultimately are available in CUDA.jl at exactly the same abstraction level. So even though it's examples written in C, typically you can port them very easily to CUDA.jl, at least at the kernel programming level. And that's the book specifically. All right, let's continue with the end of my CUDA.jl deep dive. So for now, I'm going to be doing some live coding and demonstrate the use of the profilers, which is always risky. So I have my VS Code instance out here. Let me zoom in a little. And I've put the latest version of the shared memory atomic reduction in a function, kernel function in a file, and I've written a wrapper function called mySum that's going to be doing the necessary bookkeeping. For example, it's going to be allocating a output array, it's going to be launching the kernel, well, first compiling it, then using the occupancy API to figure out a good launch configuration, then it's going to be launching our kernel, and finally it's going to be fetching the reduced value and return it as a scalar. So let me launch Julia. And one way I typically do this is using a revise, where I can just do an include t of my sum.jl file here, and then I can interactively modify code and call the main function over and over again. So in this case, this is going to demonstrate that my function works because it's going to be comparing with the implementation. Let me zoom in a little more. It's going to be comparing with the implementation in CUDA.jl. And again, the initial load time takes a second because it needs to compile CUDA.jl, but as you can see, subsequent invocations are near instantaneous. If you want to profile this, it's as easy as calling the @profile macro on the mySum function. However, if we call this now, we'll get a warning. Namely, as I mentioned, the CUDA.jl package itself doesn't provide a profiler. It only informs an external profiler to start. However, the integration with these external profilers is great, and it mentions that we just need to launch under Nsys. So let's do that. I have Nsys launch. I have Julia in a variable. I should probably remove the banner because I don't think you can see the bottom of my terminal. There we go. So what I did now is I launched Julia under Nsys. And we don't have to do anything more. If we now, again, use revise, we can still do interactive programming. So I'll be including my sum.jl file. And let's now call the main function. And what Nsys, which is short for NVIDIA Systems Profiler, is going to do, it's going to profile the function under the @profile block, and it's going to write out a lot of profiling metrics to its so-called report file. And now I can use the Nsys UI, Nsight Systems, to open up and load this report file. Now, if we zoom in a little, then we can see our kernel being launched here. Let me again ramp up the zoom level. We can see our kernel being launched here and being executed on the GPU. And if we hover here, we can see some details, for example, the occupancy or the launch configuration. We can look at how long it takes to execute certain bits of code. But to make this more convenient, something I typically do is I wrap the function I want to profile in a NVTX range. NVTX stands for NVIDIA Tools Extension, and that's a bunch of tools that makes it possible to enrich the profiler traces. So let me call this function again. We're going to be generating a new report 2.qdrep. So let's open it up. And we can see my NVTX range in there, and it encompasses all of the API calls and operations on the GPU that I execute. Now, another recommendation here is to execute your function twice, because as you'll see, the initial record can always include some overhead. Let's zoom in. As you can see here, the first execution took 325 microseconds, while the second one only took 100 microseconds. And this overhead seems to be caused by the profiler itself and not by Julia, because all of this code in Julia has been fully precompiled. So going forward, we'll always be executing our code twice under an NVTX range so that we can conveniently spot it in our profiler trace. So in terms of efficiency, this looks like a fairly good implementation of a method on the GPU. So as you can see, out of this 108 microseconds, the GPU is active for 50 microseconds. However, if we were to execute this function multiple times, then these gaps, so to speak, where we have to wait on the GPU to finish, they would lower the efficiency by which we can use the GPU. So for that, I have this small implementation. It doesn't change much. The only thing it does is instead of calling my sum, it now calls my multiple sums, which is going to be summing across one of the dimensions. So instead of 1024 by 1024, I now have a 3-dimensional input size 10, and we'll be reducing, we'll be performing the sum of each of these slices of this third dimension. And this is just the same as summing across the first and second dimension. If we now execute this, again, let me first uncomment this profiler block to show that it actually computes the expected value. It does, the assertion doesn't trip. So let's now run it on the profiler. So this interactive profiling, where every time you just get a new report, and even though you can modify code everywhere in your code base, it be in your source file or even in CUDA.jl, is a very powerful way to optimize GPU code. Have a look at our profile. And as you can see here, as we expected, as I predicted, there's gaps between each of the 10 invocations of our summation kernel. And this is not good because ultimately in this trace, the GPU is idle a bunch of times because in this case, we're waiting for a memory transfer to finish. So when we are accessing this element here, we have to wait for the GPU kernel to finish before we can copy the value to the CPU. And that kind of synchronization is bad, but it's also unneeded because ultimately we only want the result of our summation after we've performed all of them. So that's why we can perform this summation lazily, so to speak, where instead of summing and then copying back to the CPU eagerly, we'll just be summing into a GPU array. So my multiple sums now, instead of allocating a CPU array, it now allocates a GPU array of sums, and we'll just be summing into a single element view into this array of sums. And then at the end, we can copy it back to the CPU to, for example, perform a comparison. But crucially, we won't have to synchronize at the end of every invocation anymore. So let's execute this. Let's have a look at the report 5. And this is great. And as you can see, all of the gaps between the individual kernel invocations is gone. And in this case, it takes a little longer because probably there was a GC pause in between that. Yeah, this is probably, in here, there's probably a GC pause. Nonetheless, you can see that with 840 microseconds compared to 1.4 for the first iteration, we've sped it up significantly because we're effectively getting rid of the lag times between individual kernel invocations. And this is something very important if you write a realistic GPU application. If you profile it in the systems profiler, where you get this timeline, you need to have a look at where the pauses are, at which points during my applications is the GPU not being used. And you can try to avoid those pauses by making sure that the operations are still asynchronous, by not synchronizing, or by fusing operations together, or by otherwise optimizing what happens on the CPU in a way that the GPU gets used efficiently. And this is becoming more and more important because GPUs are becoming more powerful, where CPUs are too, but less so. So you'll need to be thinking more about how to optimize the CPU parts of your GPU application in order to use the GPU efficiently. Now, of course, beyond this timeline, let me just first have a look at whether there's any questions on this part of the workshop. Again, all this is also part of the, I put it with screenshots in the notebook. So even if you don't manage to run the profiler, which, for example, it's not possible currently to do so on JuliaHub, then you can have a look at these screenshots and read the explanation, which is basically what I've been telling you here. If you want to install Nsight Systems or Nsight Compute, you can just Google it and you'll end up on a page of NVIDIA where you have to log in using a free NVIDIA developer account, and then you'll be able to download it for most platforms out there. So I was first going to have a look at questions. Nothing specifically on the profiler. I'll keep the other questions for later down the workshop. So I already mentioned Nsight Systems and Nsight Compute, but I've only demonstrated Nsight Systems. So let's have a brief look at Nsight Compute as well. So Nsight Compute is a different tool by NVIDIA, and it's interesting when you want to optimize a single kernel invocation. So for example, let's go back to our original implementation where we were executing a single sum, not multiple sums. And instead of launching under Nsight Sys, we now have to launch under NV Nsight CUCLI, which is a different CLI tool, but ultimately it does the same as the Nsight tool does. It allows you to run Julia interactively while using a profiler user interface to inspect the result of your execution. So I can again use revise and include my source file. Let's launch the user interface already. If I now run my main function, you'd notice that it blocks immediately. So contrary to Nsight Systems, which generated a report file, Nsight Compute is going to wait for you to attach the user interface to this running session. And you can do so by opening NVIDIA Nsight Compute. And if we then go to attach, we'll see our Julia process ready to attach to. So let's now attach, and you can see that it's blocked in the CUDA.jl API call. To resume, we'll not only click resume, but first we'll disable break on API errors and we'll enable auto profile. This mode will automatically profile any kernel that you execute under CUDA.jl profile, which is generally what you want. So we've enabled auto profile. Let's now resume. And now it'll take a while to compile and execute the kernel again. And as you can see, the API calls are coming through, and now a lot of output is being generated. So let me close the API overview because we're not interested in that. We are, however, interested in our kernels. And as you can see, there's two kernels being profiled. This is the initialization kernel, which we don't care about. But this is our reduction kernel we're interested in. And there's, of course, two executions because we executed the mySum function twice. If we click this function, Nsight Compute gives us a lot of information to optimize this kernel implementation. For example, you can do you can have a look at the effective utilization of the GPU. You can have a look at how memory is being used, how memory is being cached, which memory buses are being, we have contention on. So again, a lot of information, and typically you will only be using this tool if you want to heavily optimize a specific kernel. Generally, you will want just to use the timeline overview, which gives you a lot of information already. But if you want to optimize a specific kernel, this is the tool you should use. And one thing you should have a look at is the source counters, because what it does, it shows you the instructions where the sampling profiler has halted. And specifically, or alternatively, this tells you which instructions takes a long time to execute and which you might have to optimize. For example, here, there's this code from synchronization.jl. Let's click on it. And of course, it's our synchronization that takes a while to finish. We can have a look at source code and how the source code corresponds to instructions on the GPU. But sadly, a lot of these instructions will just point to the code in LLVM.jl that we use to call a specific intrinsic. So that's not terribly useful. And as a result, I typically recommend to have a look at the PTX and SAS code. SAS stands for shader assembly, because the PTX code is actually very readable. It's a high-level assembly format, which should be easy enough to understand and to link back to your function. For the shader assembly instructions, you should have a look at the CUDA documentation, where for each generation, these instructions are explained, at least very tersely, what they do. So going back to our profile view, of course, a lot of the overhead is attributed, or at least a lot of the performance is attributed to the synchronization, which is expected because at some point your threads have to wait on other threads. So let's go back to our overview. What else is there? There's a store into shared memory. Unlikely we can optimize that either. It's expected that this is going to take a while. There's some, of course, our floating point addition, which is our reduction operation that we're performing in this code. So of course, that's also expected to take some time. But if we keep on going down, we encounter some instructions that we may be able to optimize, because many of these indexing instructions are being executed in the int64 domain, whereas GPUs typically perform a lot better when you use 32-bit values, both for the stuff you store. So float 32 is going to perform a lot better than float 64, but also for indexing. We can see this, that there's a lot of wide multiplications and wide integer operations that all together take a lot of time. So let's try and optimize this by switching our implementation and adding a bunch of int32 across the place. And this is not particularly nice, and typically it might not matter for more heavyweight kernels. But I'll be demonstrating it here just to show that you can compare the performance in Nsight Compute. So let's execute our function again after having replaced all of our indexing operation with int32 counterparts. Now, if we go back to Nsight Compute, we can see that now kernels 3 and 4 have entered. So we can first add this one as the baseline. Let's go to execution 4. And we can see that the total cycle count has gone down by a lot, from 82 to 60 cycles. And correspondingly, the execution time also has dropped a lot, from 50 microseconds to 40 microseconds. Just to demonstrate that you can use this overview where the program counter sampling profiler shows you at which lines of source code time is being spent to optimize the operations that you perform in your kernels. But I think that's about it. So again, all of that is demonstrated in the notebook, which is part of the GitHub repository as well, together with all of the optimizations that I've now very briefly shown. I'm going to end with a short piece on common issues, because especially if you dive into kernel programming, you might run into the limitations that the Julia GPU stack also has. The most common thing we see with bug reports being filed is that certain operations are just not supported. For example, if you use the linear algebra eigen function on a GPU array, we get a scalar indexing warning error, exactly in this case. And that's because if you would look at the backtrace, you could see that we're falling back to generic functionality from the linear algebra standard library. That generic fallback functionality typically uses for loops, which, as we've mentioned before, are bad on the GPU. This doesn't mean that we're opposed to implementing this eigenfunction. It just means that somebody hasn't come by and implemented this either in terms of a generic GPU kernel or in terms of functionality that, for example, kublas or kusolver or any other of the CUDA vendor library exposes. So if you run into a missing functionality like this, you could have a look at whether kublas supports this operation, or write your own GPU kernel using the patterns we've described in this workshop. And by all means, if you want to contribute it to CUDA.jl or GPUarrays.jl for a vendor-neutral implementation, that would be much welcomed. Another common issue is accidentally leaking a CPU array into GPU code. For example, here I have an array A on the GPU and I have an array B on the CPU. If we now broadcast A and B, then the broadcast machinery will automatically use the GPU implementation, but a CPU argument cannot be used. And as a result, we get a complicated error that warrants that we're passing an argument that's a non-bits type, because the CPU array type is not as bits. And to help you with this, we then decompose the argument in question and peek into each of the fields that are not bits. For example, here, the package warrants that the broadcast itself is not bits, which isn't very useful. But if we keep on following, we can see that there is a vector float64 being passed into our broadcast. And that just points back to our vector B and should help you figuring out why this is not supported on the GPU and what you need to do to fix it. If you write your own kernels, there are also a bunch of pitfalls, and the most common one is that you're using functionality that's not supported on the GPU, because essentially GPUs are still accelerator devices, and even though we try to support as much of the Julia language as possible, some things are just very hard to implement. For example, the print function, as I mentioned, we have @kuprint and @kuprintln, but if you accidentally use the print function, you can see that there's an invalid IR error because the IR being generated for this kernel is just not GPU compatible. We do our best to generate a stack trace that points you to the unsupported features. So in this case, this will typically surface as a runtime call that's not supported with an accompanying backtrace that shows you which function resulted in this call to a runtime function. And the print function is immediately clear from that. Sometimes it's not as clear though. For example, we have a bad kernel here because it's bad. As if we execute it, we also get a unsupported IR. And in this case, it's because an unsupported dynamic function invocation. So it's not a call to the Julia runtime, but it's a dynamic call to a function. And all calls on the GPU have to be statically resolvable. And at first sight, it's not very clear what the issue is with this kernel. And that's why we have a bunch of code reflection macros. For example, @device code warrant time, which is very similar to the @code warrant time you're probably familiar with. And if we run this code under @device code warrant type, we will get the code warrant type for each kernel being executed. And if we look at the code warrant type, it's immediately obvious that we get an any here where we expect a tuple or an integer. And if you think about it some more, you can see that instead of thread ID X, we used the thread ID function, which resulted in a dynamic function call to a unknown function. Sometimes, however, this is now a very superficial example because the error occurred in the outermost function. If it's not visible because the error occurs in an inner function, you might want to use Cthulhu because that package has a interactive mode which you can use to recursively expand functions you call and call device code warrant type on that again. And we conveniently support that using the interactive equals true argument to add device code warrant type. So if you import the Cthulhu package and then you do a device code warrant type with interactive true, you'll get Cthulhu's interactive reflection UI to find out what's wrong with your function. And of course, if you have code warrant type, you also have code LLVM, which you can use to have a look at the GPU code that's being generated. We also have function versions of these reflection utilities. So you can call CUDA.code.btx with a tuple type. Similarly with code set, which is the shader assembly I've shown in the profiler a while back. But again, typically this code is only if you want to optimize functions. Typically, you won't go beyond the code LLVM, which is a very high enough level to still be useful in terms of optimizing your kernels. Let me have another look at the pigeonhole. How portable are the profiling results between different GPUs? Once optimized on one GPU, do they hold up for others running the code? Generally, at least within the NVIDIA world, they are fairly portable. What may be the case is that some optimization might not be as pronounced on one generation of GPU. For example, as you've seen with the shared memory optimization, it might be a very good optimization for one generation of GPUs and barely change execution time on another. Nonetheless, if you follow the guidelines of the profiler, for example, by maximizing occupancy, lowering register usage, improving coalescing behavior, all of that is going to be useful for all generations of GPUs. Another question about bank conflicts and what would be a good approach to optimize a stencil operation. I think that this might surface during one of the case study implementations later on, because I know that Valentin has implemented a stencil operation in the past. So I'm going to punt that question to him later on. Right, so for the final bit of this part of the workshop, I'm going to highlight another potential pitfall with parallel programming, namely that you can also run into parallel programming issues where...
If you want to briefly demo the interactive mode, if there isn't too much trouble, there was a question just now.
Aha, yeah, I didn't include it because...
if it isn't, then we can do it just at the end.
Yeah, I'll do it at the end, because I didn't include it because the output isn't nicely rendered by Jupyter. Yeah. So the last issue I wanted to show is, for example, here I have implemented a GPU transpose function, which is a efficient transpose in that it follows the optimizations I've laid out in this workshop. For example, it uses static shared memory to buffer your reads. It tries to use as many threads and blocks as possible, and so on. However, if we execute it, we can see that our transpose is value, it is, and then another time, oh, it isn't. So we're doing something wrong here. And to figure out what's happening, NVIDIA also has a couple of sanitizers. They used to be called the CUDA memcheck tool. Nowadays, it's the computed sanitizer with a couple of modes, including a race check race detector. And this is going to be interesting in this case, because if our transposition is valid sometimes and not in other cases, this may, for example, be a race condition. It may also be a invalid, undefined memory, uninitialized memory read. But in this case, I know it's a race condition, so let's demonstrate it using the race check tool of the compute sanitizer. So to make this convenient, CUDA actually ships the compute sanitizer. So if you call CUDA.compute sanitizer, you get the path to the detected compute sanitizer. And this obviously only works if you're using the artifact installation path. If you're using a local CUDA installation, then you need to make sure yourself that the compute sanitizer is installed. So if we now put our transpose in a dedicated file and we run it under the race check tool using this invocation, then the compute sanitizer is going to detect a race between a write and a read from shared memory. Now, to explain the arguments I pass to this tool, first I pass launch timeout equals 0, because otherwise the compute sanitizer is going to be expecting you to start your kernels very rapidly, while in the case of Julia, we have some known initial latency before we can actually execute code. So it's better to set the launch timeout to 0. And we also want to disable API errors, because we use some APIs purposefully erroneously to detect whether an allocation is part of the CPU or the GPU. It's a technical detail, but nonetheless, if you forgot this option, then you'll get a lot of warnings for each of these innocuous API errors. So it's better to turn it off. And finally, we select the race check tool by specifying the -- tool argument. And what we detect here is a race in shared memory between this write and this write and this read. And we can work around that by synchronizing our threads between. And as a result, now we always get a valid transpose. The race check tool is typically valuable if you think you're dealing with a race, obviously, but the most valuable tool, especially if you're running into illegal memory accesses, is the memcheck tool. And that's also the tool that's being used by default. We're also running this tool on CUDA.jl CI. So if you have an implementation or you want to contribute an implementation and you're not sure it's fully memory safe, you can just open PR and CI will check it for you using the compute sanitizer tool. And I'm going to keep it at this because clocking in at an hour and a half, I think my deep dive have been detailed enough. And I think it's probably time for some more lighthearted case studies on how to use all of this functionality, either with CUDA.jl or any of the other GPU backends. Again, all of the code here is part of the workshop repository, and we have an implementation of it for both CUDA.jl, which is the one I've demonstrated right now, as well as AMDGPU.jl. And soon, this week at least, we will still upload an implementation for oneAPI.jl as well, which is probably convenient to many of you who have a IGP in your laptop or desktop computer. And with this, I hand the mic to either Valentin or Julian.
All right. Thanks so much, Tim. That was excellent. So let's move ourselves to the first case study, which is image processing. So in this demo, we're going to go through the
Can you
basics.
zoom in a bit and make sure that it's your full screen so that people can see it on stream?
Yes, one moment. And let me see if I can get this to zoom in properly. Give me one sec. Is that better? I assume so. Okay, great. So let's do an image processing demo now. We're going to use AMD GPU for this demo just because that's what I have available. Here, these are just some common definitions. We're loading under the hood. They're actually loading AMD GPU, as well as loading the rock kernels library and kernel abstractions, as well as a few other utilities that we're going to use to render some images. Many of those libraries are also seen here. So we're going to start with a test image. So I've got an image, a very cute image of my dog Lily wearing a hat. And we're going to do some image processing with this. So let's start off and let's put this image onto a GPU. So this will take a minute. So you'll see I'm using GPU array here. This is just an alias for rock array when using AMDGPU.jl, or it would be Q array if you're using CUDA.jl. So one thing we just need to be careful of when using GPU arrays in Jupyter, especially with AMDGPU.jl, you don't want to return a GPU array from a cell. If you do that, you'll hit scalar indexing, and doing that with a very large image like this is very slow. So just something to be aware of. And circumstances like that, where you accidentally return something or hit a scalar indexing spot, you'll really feel them when you're just sitting there waiting. So always keep an eye out for that. And often it's best to set allow scalar false when doing development. So here we've got this image. This is now loaded onto the GPU. So now we can actually do some image operations. So one of the simplest ones that we can do that doesn't require anything fancy is the negative operation. Basically, all we do here is we take every single pixel in the image and we just invert them. We just say 1 minus the current value of that pixel. Now this is being run on the GPU using broadcasting. So this, as Tim explained, is automatically compiled down to a kernel that's run on the GPU. So it's done very efficiently. So we can see we have a negative image. All the pixels are inverted. The flowers that previously were reddish pink are now green. So awesome. We can similarly go ahead and scale some of these values, and that has the effect of darkening the image. So we see this is the darker version. If we scroll back up, we can see the original is much lighter. So, you know, with a very simple broadcasting operation like this, we can dim an image, and with simple element-wise 1 minus a value, you can basically compute a negative in no time on the GPU. So it's really easy to do. So now, array operations are great. They do not work for everything. And you know, you can try to write things with arrays, but sometimes it doesn't work out well. So when that happens, we obviously now drop down to kernel programming. So in this case, I'm going to define a kernel called translate kernel. It's going to take an input image, which will be our original image that's on the GPU. It'll take an output image that we'll write to, and it's going to take a third parameter, which is the translation, which is just a tuple of integers indicating where to move the image in relation to the original positioning of the image. We're going to run this with kernel abstractions. So you see the @kernel here, and indexing using @index. So I don't believe we've gone in depth into how this works, but it's very similar to how you write a standard CUDA or AMD GPU kernel. Just a few things use macros to get at the same functionality. So we're going to run this, and what we're going to do is we're going to make a copy, not a copy. We're going to allocate a new GPU array with the same type and the same size as our original image, and it'll just be filled with kind of garbage data. That's just what happens when you call similar on an array. We'll clear it out to zeros so that it's just a completely black image. And then now we're invoking our translation kernel on the original image, as we see here. with the output image, and then with this given translation. So as we can see, the output of that is that the image has moved up and to the right. So we specified essentially in the Y direction a -500 move, and then in the X direction a move of 1,000. And these numbers are in terms of pixels. So if we actually look at this kernel to understand what it's doing, we see that we're getting two indices here. So we're using a capability that the GPU has to operate over a 1D, 2D, or 3-dimensional grid. In this case, we're doing a 2-dimensional grid because we're basing our execution on the size of the image, which is 2-dimensional. It's a matrix. So with these 2 dimensions, these basically indicate where in the image am I processing, which pixel am I working with. Because remember, when working with GPUs, when writing kernels, you are operating one thread or one lane at a time. So you really need to think in terms of that. And for image processing, that's great, because we can just work one pixel at a time and not worry about what all the other pixels are doing, unless we want to read and write to those pixels. So here we just do our translation. We logically move our current index over by the translation in the X and Y dimensions. Simple add. And then we go ahead and read from our input, which is our original image, and write it to the new position in the output. Now you'll see that we're guarding this read and write with this check here. So you can imagine that if you are a pixel at the very edge of the image, all the way to the upper right, your translation, once you calculate this, would be off the edge of the array. It would be somewhere that essentially doesn't make sense, somewhere that doesn't point to any allocated memory. Now, if you actually remove this check, you're going to get a bounds error. What'll happen is that it'll try to write there, but then some methods that we have implemented in the GPU packages will catch that and basically throw an error back to the Julia host so that you can see, hey, you can't do this. You can't write out of bounds. So it's very similar to the CPU in that sense. So we have this guard just to make sure that we're always writing in bounds. And if we're not, if we're reading or writing somewhere that we shouldn't be, this will just skip it. It will simply not do anything. And that works perfectly fine here. So let's go ahead and let's keep going and implement some other basic image processing algorithms. So let's do a scale. So similar to a translation, instead of moving an image, a scale shrinks or expands an image in different directions. So instead of a translation parameter, we have a scale parameter here. Otherwise, this kernel is very similar to the translation kernel. So here we're just multiplying the input index by the scale. We're flooring it so that we have an integer index. You could use a ceiling or you could use a round. What you choose will slightly adjust the output, but not significantly. And then we have the exact same guard and then read and write. So if we go ahead and run this, you'll notice this invocation is basically the same as before. We get an error. Now, if this did work, we would see that the image would be shrunk in the X dimension. We'd shrink it by about half. And then in the Y dimension, we'd shrink it by about 20%. You'll just have to trust me on that one. So let's see if we can get a rotation working. And these errors are easily resolvable. It's a bug when porting this to kernel abstractions, but that's not the fault of kernel abstractions. That's mostly on me. So let's do a rotation kernel. And regardless of whether this works, it doesn't really matter. Let's just briefly go over what we're doing here. So if you've ever implemented a rotation, maybe on the CPU, maybe you've done it with array programming, you often start with an angle. If we're rotating around the center of the image, which you might think of as 0, 0 on a graph, it's not exactly obvious that you can't just do a rotation. you actually need to move the image to do the rotation. Basically, you need to take the coordinates that we're operating in, which are right here. These are the input coordinates, and these are positive. So these will always be 1 or greater. So they don't have negatives. There's no 0 here. So what we have to do is we first logically move our image so that it's essentially centered at 0, 0. Then we go ahead and apply the rotation, and then we're going to go ahead and move it back to where it was, now rotated. This computation, you're probably familiar if you've done a rotation before. We're just constructing inline a rotation matrix based on the angle, and then just doing a matrix vector multiply with our x and y coordinates of our pixel to determine the new output position of that pixel. I've run this before. It definitely works, but in this case, we have an error. That's okay. We'll post a new notebook with these issues fixed after the workshop. So those 3 operations are pretty foundational to image processing. They're like kind of the big 3. They're often used for benchmarking, and they're pretty great. But let's do something a little bit more fancy. So let's say we want to blur the image. So in order to do blurring in image processing, you typically apply what's called a Gaussian filter. It's very commonly used for this operation. If you visualize it, it actually looks like a bell curve, like a normal curve. And so thankfully, being in Julia, we have wonderful libraries to pull from, such as imagefiltering.jl. So image filtering can generate for us a Gaussian kernel of the appropriate size, and we can convert this into something that works well on the GPU and get it ready to actually be applied to the image. So the operation we're going to do is commonly called a convolution. In this case, it's technically a correlation, but you shouldn't be able to tell the difference. And this is the correlation kernel. So it's very similar to the kernels we saw before. We still have an input and an output, making sure we don't read and write onto the same image. That would cause results that you didn't prefer. And then we have 2 extra parameters, basically just encoding the details of the Gaussian kernel. So we grab our indices as usual. We determine the element type of the output. This is just used to initialize essentially an accumulator. So basically the idea of what we're doing here is per pixel, you can imagine yourself as a pixel on the image. And when you're applying a kernel, you're reading the values around yourself, the pixels that are around you, scaling them by a certain amount, applying the correlation operation to the values of those pixels, accumulating all of those values that you get into a single number, and then using that as your new output value. So if you remember when I said that it's a normal curve, you as the pixel that we're centered on you are at the highest part of the curve. So you have the most contribution to the image, which makes sense. If, generally, even if you're blurring something, you still want to generally see what was at this pixel before. But you're also getting some contributions from the pixels around you. So that's just what we're doing here. And again, you're going to notice we have some guards here. We're just making sure that we don't read or write out of bounds. Because if you imagine you're a pixel on the edge of the image, if you try to read from the pixels that are supposedly next to you, but they go off the image, well, what happens? Undefined behavior. Basically, don't do that. So we skip those iterations. So here, this is just a basic 2-dimensional for loop, and we just sum up all of the values acquired by applying the kernel to our input value. And then once we're done with all of those for this single pixel, we write the output. Now, gotta make sure to evaluate the kernel. Now we're going to do the same thing we were doing before. We're going to allocate our output. We're going to go ahead and run our correlation kernel with the Gaussian kernel and the offsets that we calculated before, and just setting our range the same. It's the size as the input image. And now what do we get? We get a blurry image of a dog. So great, that was reasonably simple. Now, the great thing about this is this kernel, which is, all things considered a pretty simple kernel, can actually be generalized to basically any other kind of correlation that you want to do. So we're just going to reuse that kernel, and we're going to do what's called Sobel filtering. So Sobel filtering is basically edge detection in a sense. A Sobel filter lets you say, if I'm looking at a patch of the image, is there an edge in here? Or is there something that looks approximately like an edge? And the way it does this pretty informally is that it basically checks, looking at the pixel that I'm currently on, if I look at my neighbors, are they significantly different from me? Is my pixel more red while theirs is more blue but has basically no red? Well, that might be an edge. And it uses this intuition to basically determine where the edges are in the image, and we can render that with a few little tweaks so that we can actually see where the edges in the image are. So here, it's pretty colorful. It's kind of a lot going on, but we can see that the edge illuminated. Along here, you can see a bluish-greenish line on the rim of the hat. You can see all of the bands on the hat. You can see kind of colorful reddish edging on the flowers. And then, of course, you can kind of see the pattern in the sofa that the dog is on, which had a lot of kind of cross-hatching. So if we were to look at the original image, we can actually see these. So yeah, we can kind of see this cross-hatching. We see the bands here. And the use of this is pretty large of this operation. It's often used to do kind of a pre-processing when determining where edges are to get an idea of the general structure of an image. It's often used for machine learning pipelines. So that's it for this demo. I'm going to check to see if we have any questions. Could you implement the rotation using an actual rotation matrix? So that's a great question. That's actually what I originally did. I had an image matrix that I calculated on the host, just using CPU operations as usual, and then I converted that to a GPU array and then uploaded that, basically just passing it as a parameter, and everything just worked. It was fine. But the problem with that is, while in some ways it's more efficient than directly calculating the matrix on the GPU, you have to realize that the amount of time that it would take to create that matrix, to do the allocations, call into the GPU runtime library, and then to have the CPU do the calculation, then upload that to the GPU, have that copy happen. All of that amount of time that was taken to do that is kind of wasted. Because for the GPU to inline construct that matrix, so let's go back to the kernel, to, where is the rotation? It should be down one more. Here it is. So to do these operations, these are extremely cheap on a GPU relative to the cost that I was just describing. Trigonometric functions like cosine and sine are very well optimized on GPUs. We have what are called intrinsics, which are highly optimized methods, sometimes calling into actual hardware instructions to compute these. So, and this is the case because, remember, these are graphics processing units. These were designed to do image operations. And so trigonometric operations like these are very fast on the GPU. Constructing this matrix, or really not constructing it, simply just computing the matvec multiply, is insanely fast. So, and all you have to do is just pass the angle, single floating point number, and you're done. So in the end, it's actually more efficient to just pass the angle and let the GPU do the calculation. Now, in some cases, you may have used OpenGL. And sometimes with OpenGL, you'll just do the computation on the host and pass it. Sometimes you'll use an OpenGL API to do that on the GPU. In this case, this is basically like writing it directly into a GLSL kernel, just computing the transformation right there. But there's different approaches. If you're doing something different than a rotation, it might make sense to compute the matrix on the CPU first, especially if it's a very involved calculation that's very expensive, but you only need to do it once for the entire kernel invocation. So let's see what else we have here. So there's a question, how do you convert the image processing case study for CUDA? I see it was answered, but I just want to point out that everything I've done here generalizes to CUDA equally well, should generalize to oneAPI equally well too. So you noticed at the very top of this, I loaded some common definitions. Basically, we're just either loading AMD GPU, ROC kernels, and kernel abstractions, or we could load CUDA kernels and kernel abstractions. And then everything else would work exactly as is. No changes would need to be made to this notebook. So that's kind of a testament to the power of kernel abstractions, is that we can basically write once, run everywhere. And especially with CUDA and AMD GPU, the two that I've worked with, this has always been the case with kernel abstractions. Since ROC kernels was added to kernel abstractions, things just work. And you know, so let me actually just bring up the kernel. The amount of changes that you really need to make to turn this into a kernel abstractions kernel is minimal. It's very small. In fact, it's, in my opinion, much easier. But anyway, to directly answer your question, this can work basically as is on CUDA. And for this notebook, all you need to do is you could change this string to say CUDA and just evaluate all these cells, and it should work as is. Let's see. All right. And I think that is all of the questions relating to this talk. Let me just double check. I didn't miss anything. Yeah. All right. So Tim and Valentine, do you think now is a good time to take a quick 10, 15-minute break before moving on to the rest of the case studies?
5 minutes or so, I think, makes sense. Much longer than that, I don't.
Okay.
I think we otherwise run out of time at the end.
Okay, sounds good. I will just take myself off the stream, and I'll be right back in 5 minutes. All right. Let's get back to it. All right. So I'm going to bring up our next demo. So now that we've done some image processing, let's have a little bit of fun with arrays. So, all right. Give me just a second to make this full screen. Okay. So we all know that arrays are fun. This is going to be just a pretty lighthearted way to kind of see what we can do with them. So because machine learning is kind of hot and the big thing right now, probably will be going into the future, we're just going to implement some of the basics from scratch. So let's implement a Flux dense layer. So if you've used Flux, the dense layer is the core of many parts of large models. It's a pretty basic layer, but it's kind of good to understand how difficult it is to implement some the Flux layers to basically implement the basics of machine learning on GPUs. So let's go ahead and just create a simple dense matrix, dense layer lookalike. Excuse me. So in this, we have two arrays. We have a weights matrix, and then we have a bias vector. So if you're familiar with machine learning, you'll immediately know what these are. If you're not familiar with these, basically the weights are, if you imagine this as an analog to biological neural networks like our brains, the weights are like the synapses, the connections between neurons, and biases are kind of like a scaling factor to move things to the right level. A little bit hard to explain intuitively, but in terms of the actual operation, it's pretty simple. It's the weights times the input x, and then element-wise added to the biases. So in order to actually use this, it's really simple. So in this case, you see that we're calling GPU mod.rand8. GPU mod you can just replace with AMD GPU or CUDA appropriately, and the notebook does that for you automatically. So in this case, we're allocating an 8-wide vector of random numbers, and that's going to just serve as our input. If you're actually doing this for real machine learning, which I would recommend using Flux if you're trying to do machine learning, but you could also use this handmade layer, you would actually feed in your data points here. And these would then be used to actually feed through your model. Let's go ahead and actually construct our dense layer. So here we're going to set up our weights as a 32×8 matrix, and then we're going to set up our biases as a 32 wide vector. These again are also on the GPU. And now how hard is it to actually use this layer? It's trivial. This one-line definition right here makes it super easy to pass our inputs through and get our outputs. And you can imagine that this vector that comes out is kind of like your prediction of your model. If you imagine that this dense layer is your neural network and it's super smart and well-trained, and you plug in your data, this is what it thinks about your data. This is its prediction, or inference, or whatever you want to call it, whatever the purpose of this is. So that's pretty easy. A simple struct definition, a one-line method, and then we're going. So obviously a real dense layer does a little bit more. So what a real dense layer in, say, in Flux has is an operation, a function. So this operation is what's commonly called an activation function. And it's basically just applied to the end, at the end of the layer, to say, what do we want to do with our results? Do we want to kind of push some of them to higher values? Do we want to kind of shrink some of them down towards 0? It's kind of like that. And there's a lot of different functions that you can use for that. Now, the definition that we have for this layer is pretty simple. We just use broadcasting, and we apply our op to the results of our previous computation. So pretty straightforward. So now I'm going to use kind of a very strange activation function here. I'm going to use base.sign. And this is just to show what the GPU libraries allow us to do. So we're using basically something that's not supposed to be an activation function. This isn't a ReLU or a sigmoid or something like that. This is just some arbitrary function that we're just going to apply as an activation function, and it works perfectly fine. Now, is this actually useful to you as an output of your model? Well, it depends. Maybe base.sign is what you need, and maybe it's not. But the point here is that with broadcasting, you can basically apply whatever you want to a GPU array, and broadcasting just does it for you automatically. Now, I could have, in this example, I could have actually hacked in support for base.sign into AMD GPU, the library I'm using, and just to make this demo work, that is possible. It is not the case, but to prove it, we're going to just construct right now our own function called ReLU. I believe it's called a rectified linear unit. And it's pretty simple, and we're going to use that as our activation function. And this is probably more familiar to people who have done machine learning. Let's make sure that this is defined. And there we go. And now we have our output. And so as we can see, I didn't tell Julia how to apply this to a full matrix or a vector. I only told it, if you're given an x, if that x is greater than 0, return x, otherwise return 0. So in this case, a function that AMD GPU knows nothing about still compiles down perfectly fine into GPU code. And this instantiation does, in fact, generate a kernel with your code optimized down to as fast as it basically can be. So that works, no problem. And you could keep going on from here, building different layers, building like a flux.chain that just computes a bunch of stuff, one layer after another. And that would work perfectly well. So good luck doing that so easily in Python. So Julia and the GPU packages really just cooperate naturally to compile down these functions into something that just works and works fast. So let's see if there are any questions before I move on to my next case study. So I see there's a question that says, why do you need GPU mod.rand? Why can't rand dispatch to a GPU implementation? So that's a great question. That's actually what I'm going to address with my next use case. So GPU mod.rand technically is dispatching to a GPU implementation. The way it works is this will be forwarded to the RNG library that the GPU package has wrapped. So for AMD GPU, it's called ROCrand. For CUDA, it's QRand. And those do actually work by computing random numbers on the GPU. But at least for ROCrand in the AMD case, it's not so easy to actually get those numbers directly on the GPU while you're, say, within a kernel. But this does work perfectly fine for our purposes. This is not calculated on the CPU. These RNGs are, in fact, running on the GPU. Okay. And I believe that is it. So I'm going to move on to the next demo, and I believe this is my last one. All right, so let's get this loaded up. So not everything is peachy in kernel land. You can do a lot of things on the Julia host on the CPU that is not really so easy to do on the GPU. So the Julia host has access to a fast random number generator that you can call from multiple threads. And we're all familiar with it, rand. So as we saw in the previous demo, you can use the libraries that are wrapped by CUDA and AMD GPU to compute random numbers. And these will be computed on the GPU, although we don't really have a whole lot of evidence of that, but we just have to trust that that's the case. Now, one note is that this allocation is being driven by the Julia host. So we're initiating this from the CPU. It's eventually calling into the GPU to compute those numbers, but we're not doing our whole computation on the GPU right now. We're doing some on the CPU and some on the GPU. Now, if you use CUDA, it's actually possible to calculate random numbers directly on the GPU. So Tim implemented a device-side RNG, which works really well. I can't demo in this case because AMD GPU doesn't have it. But it basically lets you just call rand directly on the device and use it right there. And this is likely one of the fastest ways to get random numbers on the GPU. But it is currently only specific to CUDA. So we need to have a fallback. So if we can't do that, then maybe what we do is for every kernel launch, we could go ahead and allocate a random vector and pass that, or random matrix, or whatever we need, and pass that to the kernel. So in this case, what we're going to do, so say we're doing a simple in-place addition between basically taking a random number and just adding that to the current value in our array. So pretty simple. How do you do that? So we have for our kernel just the input and output array. It's the same one. And then we also have this extra argument r, and that'll be our random number that we're going to pass, our set of random numbers that we're going to pass in and use in the kernel. So this benchmarks kind of admirably, but the problem with this is that we see that, so let's actually do this for a few more iterations instead of just one, because one is pretty easy to do. But say you want to do this 100 times or 1,000 times or 1,000,000 times or just continuously as fast as you can. Well, the problem with this approach, as we can see here from the timings, is that you're making this call into this GPU library every single time, allocating more and more arrays, causing more GC activity, just to allocate, in this case, a small set of random numbers where you only need one per lane. And it works fine, but it's not necessarily great. So here we're managing about 12 milliseconds. And I'm sure in CUDA it would probably be a lot faster. The random number generators in AMD GPU are not so optimized. And some of the timing is not so accurate, but that should be about an upper bound of what it really is on the GPU. So let's think of some other strategies that we can do. So what we could do instead is we could allocate, instead of just a single vector for every single kernel invocation, we could allocate a big matrix where every single row or column is a set of random numbers that will be used for one kernel invocation. And then what we do is, so as we see here, we first allocate a big matrix of 100 by 32, not so big, but 32 is basically going to be how wide the kernel is. For one kernel invocation, how many threads are going to be active, and it'll be 32 in this case, as we see from the ND range specified here. What we're also going to do is we're going to set aside 100 random values, or 100 sets of random values for these kernels that we're going to launch. So we're going to launch 100 kernels, and each of them is going to get their own column of 32 values. So, so when we actually execute this, in order for this to work, we need to pass in an index that says which column within this matrix are we going to actually read from? Because we don't want to read from an adjacent column or all just the first column. Because if you do that, you end up using the same random numbers that another kernel is using, and that's not good. If we want random numbers, generally we want really random numbers. We don't want the same numbers that another kernel just used. So in this case, we're going to pass in the index that we use to sample from this array. And in this case, it's a very slight modification from the kernel that we saw before, where we simply just add this RIDX index in here. And we're just grabbing that here from when we generate our 100 kernels, we just say which number kernel did we just generate, and pass that in as the random index. So this works fine. It's a little bit faster, so 7 milliseconds instead of 12 to 13 milliseconds. I'm sure this could probably be optimized as well, but it's a slight improvement, but it does leave something to be desired. So say we allocate one matrix for this, but then we're generating a bunch more kernels than we could fit in a single matrix. Like maybe, we basically need enough random numbers to fill 50 gigabytes. Well, most GPUs can't hold 50 gigabytes. So what do? Okay, you allocate a smaller matrix, but then what happens when you get to the end? Do you start back at the beginning? Well, then you're reusing random numbers. So every single time you get to the end, you're probably going to want to regenerate your random matrix. So you can do this, but if you're launching, say, in this case, 100 kernels basically in parallel, well, you can't change the random numbers from under a kernel while it's executing. So you have to wait for all of the kernels to basically finish before you go updating that array. You could try to do that using some of the copying APIs available, but you'll probably experience pretty bad performance since that data is still sitting on the GPU. And it's, sometimes it's an okay approach. Sometimes this is not a great approach. But an alternative that you can do is, if you're using AMD GPU, we have something called a host call. And a host call is basically just a mechanism where the GPU can call a CPU function. So it's not any arbitrary function, but you can specify ahead of time a function that you want the GPU to be able to call. And in this case, we construct this function, which basically the body of it just allocates a 32 wide array of random numbers. And then it uses this raw convert function, which basically just makes it device safe. It's the value becomes safe to pass to the GPU. And the way this works, this kernel is modified so that instead of getting the random values passed in at the top, we instead just pass in this HC, this host call value. And what that allows us to do is actually call that CPU function and get back a value. And in this case, R is our array of random numbers that the CPU generated for us at the time when we needed it, not beforehand, immediately when we needed it. So this approach, now you can see this approach is not actually fast. It's simply an alternative, and it really needs tuning to be effective. But this kind of shows the possibilities that you have, at least with AMD GPU's host call. You can do fancy things like call into the CPU when you need things from the CPU instead of passing everything in as a parameter, or the alternative, which I wouldn't recommend in this case, implementing an RNG on the device. Now, if you're going to do that, if you're going to implement an RNG by hand on the device, I would hope that you know what you're doing, because it's not easy. And especially if you're doing something security sensitive, it's probably not a great idea to hand roll your own random number generator. You're probably better off just using the vendor's random number generator library. But at least here we have some options to do things a little bit differently, and to kind of have the GPU do a little bit more of the work and alleviate the CPU from having to do everything up front. So that is it for that use case. Hopefully host call will be useful for people in the future. And there's certainly room to improve it and to make it a bit faster. All right, well, I think that's it for me. Valentin, I am going to hand this over to you.
Thank you, Julian. And I will cover the rest of our time and talk a little bit about kernel abstractions, some of the finer details, and hopefully how you can use it yourself effectively. So let me share my screen. And let's do this. Okay, so these are, the notebook is in the subfolder kernel abstractions. And at the beginning, you can basically choose which backend you want to execute your code on. You can select CUDA, that's the GPU I'm going to run on, or as Julian has demonstrated, you can also use AMD. Or if you don't have a GPU, you can also execute kernel abstractions code on the CPU. And quite a few of the peculiarities of kernel abstractions actually stem from this fact that we also support CPU execution. Just as a note, if you're running this in a Jupyter notebook, you can use the iJulia package to create a Julia notebook that will have multi-threading enabled, and then kernel abstractions will actually use that multi-threading automatically. Then, if you're executing the notebook for the first time, comment out this part beneath, which will install kernel abstractions and the necessary packages. I already done so, so I just activate the backend, the environment in the backend. I can then load the packages, and this is basically what's hidden behind the commons definition in Julian's notebook, where we basically select, okay, we want to use CUDA or AMD GPU as our primary array implementation package. We then want a shim package that adds kernel abstraction functionality for these backends, and then we choose which array type we're going to run on and which device type we're going to execute on. And if we're going to execute on the CPU, all our, we're just going to use base array. So Julian already showed off a kernel abstractions kernel in his demos. But basically, it is a function that starts with the @kernel macro. It takes some arguments in. And inside this @kernel macro, there are a couple of verbs that you're allowed to use, functions that are all declared as macros. So there's the @index macro, which will calculate you the correct index of the element you're currently operating over. And there are also different different scopes of indices. So you can have a global one, which is in respect to what is called the ND range, which we will get to in a second. You can ask for a group index, which is the current work group executing, and a local index, which is the current thread within that work group that is currently executing. There are also different styles, which we will cover at the end. And so this is the classic, I want to multiply a scalar, a vector times a scalar, and then add a scalar to it, implemented in kernel abstractions. So one of the questions is, well, this index seems kind of magical. So how is the index actually derived in the end? So when you launch a kernel abstractions kernel, you have two keyword arguments. One of them is workgroup size. The other one is ND range. And those specify how these indices are calculated. So the workgroup size is a local block of threads, and those threads are co-executed, and they have access to a shared block of memory. And the ND range specifies the global n-dimensional iteration space that you want to iterate over. So for each point in your n-dimensional iteration space, one thread will be executed. And so the space will be then subdivided into chunks of workgroup size. So as an example, if I say I have an ND range of 128, and my workgroup size is supposed to be 16, I get that this ND range will be subdivided into 8 individual blocks. Each of these 8 blocks has 16, and the iteration space matches evenly, so I can divide without the reminder, and therefore I do not need to execute a dynamic code check whether or not I'm in bounds or out of bounds. Now, if I have a higher dimensional ND range, like this one, I can, when I execute it, I only specify the first dimension in my workgroup size, and you can see I'm getting a 3-dimensional block configuration. And if you take the product of that, we would see how many blocks are going to be launched. But we can also see that the dimensionality of the workgroup size is actually going to be expanded out, and there's going to be implicit ones at the attire. And so I could say, oh, I want to actually do a 2-dimensional division here, and I then get the corresponding result. But note, since the numbers are evenly divisible, I also don't need to execute a dynamic. Don't need to do a dynamic indexing check. Now, if I were to say I wanted to have a workgroup size by 16 by 15 for whatever reason, you would see that now my dynamic check is actually a dynamic check, and therefore the code that I'm going to be execute needs to be a little bit more bookkeeping to make sure that we don't execute overhanging elements in our ND range. Okay, so that's basically how partitions work, how a partition under the hood is working, and how these keyword arguments that we're going to use for the launching of our kernels are going to be translated into an actual GPU execution. In order to start, I need to instantiate my kernel. So I take the function name that I gave my kernel, and instead of passing it the arguments that I'm going to pass it later, I'm actually just going to pass it the device it's going to be constructed for. And so I then get back a kernel object, and that kernel object has metadata information associated with it. So I know here that it is going to be a CUDA device execution. It doesn't know anything about dynamic size, it doesn't have any size information associated with it. And we will get to this in a second. And then at the end, you see this little bit of hidden metadata, which is that there's actually a corresponding Julia function under the hood that we will execute and compile for the GPU. Now, if I'm going to use adapt to do some allocations on the host and then move them over to the GPU. And then I'm going to execute this kernel and say, okay, my array set is going to be my output, and x and y are going to be my inputs, and my alpha scaling variable is going to be 0.01. You get this error message that the kernel cannot be partitioned. And the reason for that is that you are lacking information. So you either must provide static information at the time when the kernel is being constructed, or you must provide dynamic information at the time the kernel is launched. You can choose between them. And it tells you all of the information it had. It couldn't partition your kernel, etc., etc. Okay, so let's actually provide dynamic runtime information. I'm going to use the size of my Z dimension to specify how many iterations I want to run. And I'm going to manually choose that I want to have a workgroup size of 32. The first time I'm going to execute this code, quite a bit of code is going to be compiled. So the first launch here, right, that took about 6.7 seconds. When I do it the second time, launching is quite a bit faster. I can also leave the workgroup size up to the backend, and backends have different policies here. Like the CUDA backend will use CUDA's auto-tuning. I think the ROCm kernel backend has a fixed group size right now, and as well the CPU backend uses, I think, a group size of like 1024, something on that dimension. So instead of providing all of these information at runtime, I can also provide this information at construction time of my kernel. And you can here I'm going to construct my kernel with a static workgroup size of 16. Now, if you look into the metadata that is associated with this kernel, you can see here I actually have now static size information available. And we're going to use that static size information to specialize the kernel compilation to that. So if the launch configuration you're using changes often, you should not use static information because it will trigger a lot of compilations. But if the launch configuration that you're going to use doesn't change often, or you might only change the ND range dynamically, then you can use static size information, and you will generally get faster kernels because that accelerates some of the index calculations we need to perform. You can then extract the iteration space and whether or not the kernel is going to be dynamic, providing it the runtime information. So here this is the ND range argument, and this is saying that I'm not going to provide any runtime workgroup size. And I can actually look at the block space, etc., that is going to be spanned by this iteration space. Right, so I can go a step further and say I'm going to only accept static kernels, static ND ranges of this size. That is much less common than providing static workgroup sizes, but sometimes useful. On the CPU, this code will error. On the GPU, it won't, because I'm providing a mismatched iteration space. So that's something I need to fix. So I'm going to pause here for a second, check whether or not there are any questions on Pigeonhole about iteration spaces. There's a question whether or not a kernel abstraction could be one day used with TPUs. Maybe that really depends on how the TPU ecosystem is going to evolve. Okay, I don't see any further questions. Please feel free, while I'm continuing with this notebook, either follow along or ask questions or pigeonhole so that I can see them there. Right. So if you had eagle eyes and you looked very closely at the results we've gotten so far, you might have noticed that every time we executed some code, we got something called event. In this case, because I'm executing on a CUDA GPU, I've gotten a CUDA event. Now, every kernel abstraction kernel launch is going to execute asynchronously with respect to the host and with respect to all other kernel abstractions kernels. So if I launch this kernel 20 times in a row, some of those kernel executions might have overlapped. And so I might have had a write conflict on set because I'm writing to set. And I could have gotten corrupt answers. In order to avoid that, I need to wait on this event. So I can say here, wait. And now this kernel will actually execute, and we will wait on the host for this kernel to finish before we continue. So this leads to a little bit of a tricky situation. Basically, we have multiple asynchronous sources. So as an example, CUDA since .jl since 3.0 is now using asynchronous allocations. So the allocation on the CUDA array is actually going to happen on a stream. And we are moving data from the host to the device. So we need to insert a barrier on the stream that CUDA.jl is using, so that our kernel does not execute while the CUDA.jl code is actually still executing. So I can launch my kernel, and I have another keyword argument here, which is called dependencies. And I can either give it a single event, or I can even give it multiple events if I have multiple sources that I want to wait upon. Now, it depends on a little bit. So if I don't pass any dependencies in here, right now for the CUDA backend at least, the default is to actually synchronize against the CUDA stream just to avoid common sources of errors. But if you're doing your own dependency management, you will need to insert one of these device events that I'm creating up here. Now, after my kernel is launched, it returns a kernel event to it. And so there are a couple of scenarios here. If I want to read the data set on the host needs to wait for the kernel event. And so that's what this normal wait call on this kernel event does. And then afterwards, it is legal for me to read the data from set. Now, in scenario B, I'm actually going to launch a second kernel. And that second kernel is going to use the data from C as an input. So now, if I would not synchronize my kernels through the dependency mechanism, the second kernel would read data from set that is not correct. That is stale data and has not been yet updated. Or it would start overwriting data in X, while the previous kernel is still trying to read from X. So for that reason, I need to specify a dependency event on the previous kernel event, and that will synchronize my execution. Similarly, if I then want to use X again afterwards, I will need to wait on the kernel event. The third scenario is afterwards, I want to use the data as part of GPU arrays, CUDA.jl, AMDGPU.jl execution, and therefore I need to then add a wait that is device dependent. And so I will create a wait on the stream, on the mechanism that the device package will use in order to synchronize execution depending on my kernel event. So this is also in CUDA.jl recently, because it has been a question of how do we integrate the CUDA stream design into the package elegantly. CUDA.jl now uses Julia task local streams. So every concurrent Julia task, every execution of CUDA code on that task will use the task local stream. And so if I do multitasking in Julia, I can get automatically concurrent CUDA GPU execution. That's very powerful, and it's a very nice interface. Kernel abstraction predates that, and that's why this dependency system works a little bit different. If you're writing kernel abstractions code, you don't need to change the way you're working with CUDA, since these waits here now, this wait on the device and the event device, will actually use the task local stream. Just as a note to watch out for that. But as an example, what could happen is you need to think about on which task did my allocation happen. Did I synchronize the GPU after the allocation, or is the allocation happening on a different task and therefore on a different stream? And can I already use the data? So it becomes a little bit of a complicated dance. So the best thing to think about is to say one stream, one set of data, one task, one set of data, one series of CUDA operations to execute. Okay, so for now we only talked about a minimal kernel abstractions kernel, then how to configure and launch it. Assuming that, so there's a question right now about scheduling. Assuming that I don't have any data races between my kernels, would I have to take control of the scheduling, or does CUDA something else do it? If you do not have any data races, then you can just schedule code, launch code as much as you want, and it will be executed completely concurrently. If you're using kernel abstractions, if you use CUDA.jl, they will be executed in launch order. Okay, so the actual motivation behind kernel abstractions was not necessarily to have this dependency system, but actually to access the memory hierarchy on a GPU in a device-agnostic fashion, and to execute that code on the CPU. So before I talk about this, let's take a quick look at the diffusion.ipython notebook. So this is just a quick and dirty notebook that Julia and I wrote yesterday, where we are trying to do a heat diffusion, solve a heat diffusion equation on with array programming in Julia. And so we're going to use offset arrays. We have a little bit of a hack here that we need to do to make all of that work nicely. We configure our calculation. We calculate a time step. We set up a grid space, a grid size here, and then we have this diffuse function. And this is a stencil code. And as a stencil code, what that means is that I'm going to operate over a central point, and I'm going to access my neighbor data. So I'm going to access the data point above me, right next to me, left to me, and below me. And so these funny looking, so first thing to note is in offset arrays, why are we using offset arrays? Because we have a boundary around our actual data at the index 0 and at the index n+1. And that boundary zone is called a ghost cells, and those ghost cells can be used to implement various boundary conditions. And as an example, mirror the data, and they make implementing the actual kernel simpler because we don't need to think about what will happen if I need to access the data element to my right, but I am the last data element to the right, so any access would be out of memory. It's solving that kind of problem. And so these funny-looking views here are just really shifting the underlying data one time up, one time right, one time down, and one time left. And then I can compose those different views with a singular podcast expression and express the diffusion equation. And after I did this shifting, it is really just one line of code. And then afterwards, I can update my boundary condition. And here I'm implementing a wraparound. So I'm copying the data from the nth column to the 0th column, and from the first column to the n+1 columns. That's just a brief walk through that notebook and why what we're doing here. And why I'm talking about this is because the next kernel we are going to look at is going to implement this diffusion kernel. Instead of using views, it is going to use a kernel abstractions kernel. And so you see something similar here. Instead of using views, we are just using direct indexing. And so this is the same thing with the one up, one left, one right, one below, and where we we'll be collecting all of the data elements. And then we have a similar equation, but instead of having it as a podcast equation, we are having it as like a scalar equation. And then we update the data element. Now, stop for a moment and think about, are there any data races in this code? While we think about that, I will just go through the rest of the cells, which again are very, very similar to the other notebook, setting up everything, configuring the offset array, instantiating my diffusion kernel, and then I want to execute my diffusion kernel. So two things that are wrong with this kernel. One of them is data races, and the other one is the data access pattern. The data race is actually between different blocks of CUDA code, kernel abstraction code executing in concurrently, right? So you're going to have one block executing, and you're going to have a second block executing. And since we're looking at the neighbor code, we're actually going to look at the data i, here of our neighbor. Now, depending on how the execution happened, that thread block might have already run. And we read the new data instead of the old data. So instead of having our data operation happening in a way where, independent of execution order, every read from data i, j or i-1, j reads the same element. Now every read might read the data from the next time step already. And that can lead to all kinds of funny issues. So one way of solving this is a strategy called double buffering, where instead of reading and writing to the same array, I read from one array and I write to the other array. And therefore, I avoid these issues with interleaved executions, reading different data steps. The second issue is data access patterns. So GPUs like very regular data access pattern. And here we are accessing data in this 5-point stencil kind of fashion. And we're going to issue global memory reads. And our neighboring threads are going to execute as well. And they're going to execute the same set of reads. And some of them will overlap with my own thread. And so basically, we are issuing too many of these reads. And the GPU is going to look at this, and it's going to first respond to this read request for every data element, and then for the shifted one. And it doesn't really know that there might be overlap in these reads. And then it gets even worse with reading above and below, because those are in different memory region. And so the data access is passed is data access is you're loading about 5 times too much data. I think that's the right calculation. So one way of fixing this is to use local memory in coding abstraction parlance or shared memory in CUDA.jl parlance to cache those reads. And so I can set up a local memory buffer, and I'm going to set it up 2 elements too big, because I need to read in my ghostals. I need to read in my boundary as well. And so you see here now I'm using a global index, and I'm using the n-tuple style. And then I'm going to use a local index and the n-tuple style. And really, a global index is going to be used to index global data, and a local index is going to be used to index local data. I'm going to set the element type to be the element type of my data array. And I'm going to use the add_group_size macro to query the kernel configuration. And then I'm also going to annotate in my kernel code to say that this data array will only be read. Inside this kernel, I will not write to this array. And that means, depending on your architecture that you're executing on, you get a more efficient kind of read. Then we need to do a little bit of annoying bookkeeping, which in this case is basically we're going to copy the data over. We're moving from the global index that we're responsible for to the local index that we're responsible for. Now, we are going to copy over the boundaries as well, and we are not responsible for those boundaries. So if we are the first index, then we have to also copy in the data left of us. If we are the rightmost index, we also have to copy the data in right of us, and so forth. We're going to store that data in the L data array. And then we're going to call synchronize. Synchronize is going to make sure that any read from L data will read a consistent result. So it makes sure if I didn't have a synchronize here, I could read non-initialized data from L data. So synchronize makes sure that that all of the data loading is finished. Now, you also might have noticed that I put an add uniform here, and I'm actually using an offset array over my LMEM buffer. So add uniform is one of these quirks of kernel abstraction that come about from having to execute this code on the CPU as well. We basically have to tell it that this L data object is being shared across all of the threads within one group. And so that's why I needed to put add uniform in front of it. And then after I'm done, now instead of using data, I just use the local cache L data. And all of these reads are now fast because they're going against local memory. And then I'm doing my calculation as I had before. And then I'm white out to my second buffer, which is my output array. And it is this access to local memory that really is, if you're writing performant GPU applications, that is necessary. And on the CPU, when you execute the code on the CPU, we will have to simulate those features. So we will create an M array that is representative of this local memory region. Okay. So index kinds, you've seen me use primarily n-tuple or none. So the default index type is a Cartesian index, which is just an n-dimensional index. An n-tuple, I always have to know what is the dimension that I'm going to use it. And this is why static configuration is necessary for these kernels. Also for group size. If I can provide the kernel instantiation a static kernel size, then this group size code will be cheap. And then the last index type that exists is a linear index that you can use that makes things simpler. And then I can execute my code and be confused a second why my code broke in between A and B. Did I not execute this? I don't think I executed this. Okay, let's set this up first. The perils of notebook programming. Okay, I'm gonna skip that in the interest of time, and sometimes you get very annoying error messages from kernel abstractions. I'm deeply sorry about that, and I hope you can help me avoid better error messages. Okay, you can also use the add_print macro to print from within a kernel. This could be extended to actually add formatting of what we're going to print, but this is good enough in a pinch if you need to do print style debugging of kernel code. And if you're ever interested in how kernel abstractions actually work, just use macro expand over any of your kernels, and you get some interesting output. And we also have some reflection code that allows you to inspect the type invert code. And this is what I would use to figure out why my notebook broke earlier. Now, we are almost at the end of the hour. With that, our workshop is going to be over. I have a sneak peek on my JuliaCon talk about Enzyme. Enzyme is an auto-differentiation framework. And one of its key features is that it operates over LLVM-IR, and it uses the GPU compiler infrastructure to do so. And so because of that, we can actually use Enzyme as an auto-differentiation framework for GPU code. And we can differentiate parallel code in general, and that is joint work with William Moses and a couple of folks from Argonne National Lab. And if we take this example where I vote a very basic matrix multiply kernel, and I want to manually differentiate through it using an AD framework that doesn't have any knowledge about what this kernel actually does. So it needs to go in and trace every operation that is happening. Now, in contrast to Zygote or any other differentiation tool in Julia, we can actually deal with mutations, and we can deal with GPU style code. So I can create my matmul kernel, I can create some inputs, execute it, make sure that the output is what I expected it to be, and then I can use this package, kernel gradients, that I'm currently in the progress of making sure that it works well, to call autodiff on the instantiated kernel. Now I get an adjoint. I need to allocate some data to put in what we call the shadow or the differential return. What that is, I invite you to come to my talk on next week. I forgot which day it is exactly. And you can now pass in the adjoint, the shadow of C alongside the previous variable, and now at the end, Enzyme will actually update the data in these shadows, and you can confirm that you would get the answer approximately in dA what it would have been to calculate the gradient of dA analytically. And with that, I am done, and I'm going to answer some more questions if there are any. And maybe Tim and Julian also want to join me.
We have a question. Can you also talk about the future directions of backend generic programming, KA, etc., and the GPU stack?
Yeah. So one of the decisions we need to make, or we need to figure out what is the right strategy for us is, as an example, do we want to maintain kernel abstractions dependency system, or do we want to replace it with something that looks a lot like CUDA.jl's task local streams? If we do the latter, then we can go move forward with one of our long-standing goals of actually using kernel abstractions as part of GPU kernels to implement generic GPU functionality. So that's one of the big open questions that we haven't agreed upon necessarily in any direction. I don't even know what I want to do with that regard. Other than that, I think it would be great to have oneAPI backend for kernel abstractions. That's currently missing. Then over time, I want to move. You saw some of the errors are quite incomprehensible that kernel abstractions can spit out. That is partly because we use a toolkit called Cassette, which is very powerful, but it also does a lot of transformations that then lead to these kinds of errors being not understandable. So long term, I'm looking at options to replace Cassette in order to actually do the implementation slightly differently in the background. But that shouldn't change any performance. That shouldn't change any functionality. Hopefully that will work, and then we will have better error messages. Other than that, maybe Julian, tell us some goals and plans that you have for the AMD GPU infrastructure.
Yeah, so for AMD GPU, I'm trying to get as many of the ROCm libraries wrapped as possible. So right now we have BLAS support, we have RNG support through ROCRAN, and we have FFT support. And then there's been a PR posted for sparse matrix support. So all of those sparse matrix support, of course, we want to see that merged soon. And then all of the libraries, we really just need to keep hammering at getting as many methods wrapped and exposed via idiomatic Julia methods or functions as possible. And then there's also so-called ROC elution, which is basically iterative solvers. And we also want to add wrappings for that. And then the one that I'm sure everyone is waiting for is MIOpen, which is machine learning, essentially the cuDNN of the ROCm stack. And that is one that, myself included, I think everyone really wants to see. So getting that wrapped, getting good machine learning support, I think those are going to be the main goals for the next few months.
And we should emphasize, we really welcome contributions. And so if you're interested in using AMD GPU on your system and you have one of those use cases that is not yet covered, it shouldn't be too hard to get started and actually contribute some of these wrappings. It actually helps if you're a little bit of a domain expert, because we sometimes look at these things and don't quite know what they mean. But yeah. And Tim, any closing words and plans for the CUDA.jl ecosystem?
Not so much for the CUDA.jl ecosystem. So it's at this point a continuous development and looking into API improvements to make it easier to work with CUDA.jl. For example, recently the whole redesign of the task system and how to synchronize tasks. As a result of that, we will probably be improving multi-GPU capabilities. That's one of the elements that's currently still missing to make it possible to, from within a single node, use multiple GPUs effectively. And the work where we've decoupled the task local storage from the current task and stream and device is in preparation of that. And I'll be explaining that in my talk next week or so. And on the oneAPI front, the major improvement is similarly to AMD GPU going to be adding wrappers to much of the vendor packages, because currently we don't have any of them. So oneAPI.jl is completely based on generic GPU functionality, which isn't always as optimized. For example, the matrix multiplication in GPU arrays is fairly slow. So that will be a work in the future. But other than that, I think most of this has been said. I'm having another look at Pigeonhole, but if there's no other questions, I think we can close this workshop.
Yes, thank you all for joining us, and I hope you enjoy the rest of JuliaCon. We're going to have a couple of days of workshop, and then a full program at the end of next week.
There is also a birds of a feather. So if you
yes.
are a GPU user and you have any specific questions or thoughts on the ecosystem, you're always welcome on the GPU Discourse or the GPU Slack, of course. But the birds of a feather is the great opportunity to discuss these things with us. So see you then.
See you there, and have a good evening.
Thanks so much.